Hey, Math 206 students, here we go, another lecture. Previously, we've been discussing augmented matrices, and those showed up in the process of solving linear systems. Matrices on their own, not just connected with linear systems, are an important aspect of linear algebra, in fact, an extremely important aspect of linear algebra. So what we're going to do now is talk about matrices on their own without any relation, without any connection to linear systems. So we start with the definition. A matrix is a rectangular array of numbers. So what does that mean? If you take a bunch of numbers and arrange them in a rectangular shape, we call that a matrix. Matrices are typically denoted, so matrices, that's the plural of matrix. Matrices are typically denoted by capital letters, capital A, capital B, capital C, etc. Now, if the matrix capital A has m rows and n columns, then A is an m by n matrix. So here I want to focus on the m by n part. The first part, the m tells you the number of rows, the n tells you the number of columns. So for example, A, and what we do when we write down a matrix, as before, we'll put square brackets around them. So 1, 3, 2, 1, 0, 1, minus 1, 4, 1 half, 1, 0, 0. Here's an example of a 3 by 4 matrix. It's got 3 rows, 4 columns. Well, let's say capital B, another example of a matrix. How about 1, 1, 1, 1, 0, 1. B is a 3 by 2 matrix. All right, so just remember, so just remember the first number tells you the number of rows, second number tells you the number of columns. So the general form will be, right, so when we want to talk about a matrix, just an abstract generic matrix, what we'll have is A equals, and this is the numbering system for entries in the matrix, A11, A12, A13, dot, 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 up to A1M, A1N. These are the entries in the first row, and remember, this is the same that we talked about before when we double subscript. Now, the first number is going to tell you which row it's in, and the second number is going to tell you which column it's in. So, for example, A13, that's the entry in the first row and the third column. So then the next row would look like this: A21, A22, A23, dot, dot, dot. Eventually, you get to A2N. And you keep going, so if this is going to be an m by n matrix, then the last row will have entries A sub m1, A sub m2, dot, 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 eventually A sub mn. So there's the generic form of an m by n matrix. A sub ij is the ijth entry. There's a compact form. Sometimes I don't want to write, we don't need to write out this generic form right here. Sometimes I want to talk about an abstract matrix, just some random matrix, m by n matrix. I don't want to write this entire thing, so compact form. I would write A equals square brackets A sub ij. Now what this means is A is an m by n matrix whose entries are labeled A sub ij. Oh, another thing, so sometimes I like to talk about a particular entry from capital A. So notation, if we want to talk about, and we'll use this in a little bit, if we want to talk about the ijth entry of capital A, we'll write it like this. All right, so parentheses around the capital A, sub ij says, tell me who the ijth entry of the particular matrix is. So let's try an example here. So let's say capital A is the matrix 1, 2, 0, 1, minus 1, 3, minus 2, 1, and 4, 7, negative 3, 0. All right, so here's a 3 by 4 matrix, capital A. Using this notation right here, what we have is capital A parentheses sub 2, 1. So what is that saying? It's asking for the entry that's in the second row and the first column. So A sub 2, 1 is negative 1. A sub 3, 3, parentheses, A sub 3, 3. Okay, so that's the entry that's in the third row, third column. So that's equal to negative 3. Let's do one more here. How about A sub 1, 4? Let's see, so that's asking for the entry that's in the first row, fourth column. So that's equal to positive 1. So this is just some notation. When you want to identify a particular entry, you can use this parentheses stuff. Right, so there's a couple of special matrices also. So an m by 1 matrix. So what that means is it's going to have m rows and 1 column. So this is a column vector. You can also do so a 1 by n matrix. So let's see, that's going to have 1 row and n columns. So this is a row vector. I think your book sometimes refers to them as column matrix and column vector. I'm sorry, column matrix and row matrix. I don't usually use that notation, so I'll just say column vector or row vector. Now, typically, vectors, either the column vector or the row vector, rather than using capital letters, capital A, capital B, those are typically denoted by bold-faced lowercase letters. So typically vectors are denoted by lowercase bold face letters. On the board, obviously, I can't do boldface, so if I want to talk about a vector, I'll put, so let's say if I want the vector u, I'll put a little arrow over that. So in the book, this would be boldface. Or maybe vector x, I'll put a little arrow over to indicate that I'm talking about a vector. So for example, maybe we've got the column vector 1, 2, 3, 0. That would look like that. How about the row vector? Let's call this one x. 1, 0, 1, 3. a little bit more notation, or terminology, I guess we would say. In the case that we have the same number of rows and columns, that's called a square matrix. So an n by n matrix is a square matrix. What else? Oh, the entries a sub 1 1, a sub 1 2, a sub 1 3 dot 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 up to, oh no, sorry, that was a mistake. A sub 1 1, a sub 2 2, a sub 3 3 dot 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 up through a sub n n. These entries lie on what's called the main diagonal. So these entries right here make up the main diagonal. So yeah, let's draw a picture here before. So here's an example of a 2 by 2 matrix. So here's a square matrix. Let's say A equals 1 minus 1, 3, 2. Right? So the entries on the main diagonal, those are the ones that run from upper left down to lower right. Right? So A11 and A22. There's the main diagonal in that case. Here's another one. So B, let's do a 3 by 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. The main diagonal then is right there. It's the one that runs from the upper left to bottom right. And the entries along there, 1, 5, 9 in this case. Okay, so we just introduced this idea of matrix. Now we want to see what we can do with matrices, right? Why are they useful? Why are they used in linear algebra? So what we want to discuss now are matrix operations. So let's let A and B be m by n matrices, and I need a real number, so let's see, and let C be a real number. I'm going to define 3 different operations. The first, the sum of capital A and B. So we're defining what it means to add 2 matrices together, and we're going to do it in the obvious way. So this is the m by n matrix, which we'll write as capital A plus capital B, defined by. So now, what do I need to do to tell you who this matrix is? I need to tell you who their entries are, right? So it's defined by A plus B sub ij. So I want to tell you who the ijth entry of A plus B is, and it's done in exactly the way you'd expect. Oh, it's parentheses here. A sub ij plus B sub ij. So what is that telling you to do? Add the ijth entry of A to the ijth entry of B. Put those together. That is the ijth entry of this new matrix A plus B. Part B, the difference. Of A and B. So now we're defining what it means to subtract one matrix from another. So this is the m by n matrix, which we'll write, doing the obvious thing, A minus B, defined by. And so now I need to tell you who the entries of A minus B are. So A minus B sub ij is equal to A sub ij minus B sub ij. So what does that mean? To find the ijth entry of this matrix A minus B, take the ijth entry of A, subtract from it the ijth entry of B. Okay, and then there's one more. The product little c times A is defined by, let me say this better. So this is the M by N. I hate how I worded this. I'm going to reword this. The product, start over here. So the product of C and A is the M by N matrix little c times capital A, defined by so once again I need to tell you who the ijth entry is. So C sub ij, CA sub ij is C times A sub ij. So how do you do this operation right here? Take each entry in capital A and multiply it by little c. This is also referred to as scalar multiplication. So CA is, how do I word that? No, CA is a scalar multiple of capital A. So let's try one quick example. And so notice, to do these three operations that we've discussed here, what you need to do, sorry, I just stepped out of the shot. What you need to do, you've got to have matrices that have exactly the same size. So they both need to be M by N matrices. So, for example, let's let A equal 1, 2, 1, 0, minus 1, 0, 1, 1, 3, 4, 1, and 0. Notice that with most of the matrices that I do, I use integer entries, right? So I don't want to deal with fractions and decimals and so on. There's nothing wrong with having them. But just for ease of doing the examples, for the most part, I try to avoid fractions. Notice that the example I did yesterday, what was it? Solving that the linear system, it did end up with answers that had fractions. But for the most part, when I do my examples, they're going to just have integers for entries. That doesn't mean that they have to. And in the book, sometimes you're going to see where they definitely don't have integers. So now, and I'm just making up another matrix here, so I need to make up another 3 by 4. So let's go like this, minus 1, 3, 0, 0, 1, 1, 4, minus 2, and 0, 1, 0, 1. All right, so here's our two matrices, and now A plus B. So how are we going to do this? Well, remember, what you do to compute A plus B, you take corresponding entries and add them together. So A plus B is going to be a 3 by 4 matrix. And so what do we get when I add 1 plus minus 1? I get 0. 2 plus 3 is 5. then I'll get a 1 and a 0. So what did I do? I added 2 plus 3 to get the next entry. Then I did 1 plus 0, 0 plus 0. Now we move to the next row. Looks like we're going to have 0, 1, 4 plus 1 is 5, negative 2 plus 1 gives us negative 1. I'll have 3 plus 0, so that's a 3. 4 plus 1 is 5. 1 plus 0 is 1, and then a 1. Right, so there's A plus B. Nope. I want to do A minus B. So now I'm going to subtract entries. So we'll have 1 minus negative 1 is a 2. Negative 1, 1, 0. Minus 1, that'll be a negative 2, negative 1, negative 3. 1 minus negative 2, so that'll be a positive 1. Then we'll have 3, 3, 1, and negative 1. And then, let's do an example of scalar multiplication. Let's say I want to do 3 times A. So what do? I take each entry in A, multiply it by 3. So that would be 3, 6, 3, 0. Negative 3, 0, 3, 3. 9, 12, 3, and 0. Okay, so there's 3 operations, easy to define, and they're fairly obvious, kind of self-explanatory where these came from. Adding matrices, subtracting matrices, multiplying a matrix by a constant. All right, so there's one more matrix operation. Maybe the most important one for this class is the one that's about to be defined. That's matrix multiplication. So this kind of deserves its own discussion. So, matrix multiplication. So let's let A be an M by P matrix, and let B be a P by N matrix. All right, so there's the setup. If I want to multiply A times B, the dimensions of the matrices have to look like this. A has to be M by P, and B has to be P by N. So now, the product of A and B is the M by N matrix, which we'll write as A followed by B, so A times B, defined by, so now I need to tell you who the entries of this new matrix are, and it's defined by, and so I need to tell you who the ijth entry of A times B is. And the formula is, it's not what you expect. All right, so I want to write this down. So this will be the sum, K equals 1 to P. A sub ik times B, parentheses, right spot here, times B sub kj. So you just need to kind of stare at that for a minute. It is not the formula that you expect, because you would think there's easy ways to define matrix multiplication. this is a complicated looking formula. All right, so we're going to need to sort of think about how this goes, talk about it in various ways to see actually how it works out. So here's the idea then. So what do we have? So I'm going to kind of take this slowly. Here's my matrix A, and so this one was M by P. So here's my matrix capital A. Here's my matrix capital B. This matrix is P by N. And then, so here's the thing to remember. When you have an M by P times a P by N, then you're allowed to multiply them. So you've got to have matching P's right here. And when you're done, what you end up with is the matrix A times B, and that matrix is an M by N matrix, right? So the way I've always thought about it is sort of the P's cancel out, and what you're left with is an M by N matrix. Now, how does this go? Well, so yeah, what's happening here? So let's look at this formula. K is going from 1 to P. So that means that for the ijth entry, what we'll be multiplying is, when K equals 1, we will have A sub I1 times B sub I, let me say that again. The sum, so K is equal to 1, so we'll have A sub I1 times B sub 1j plus A sub 1, 2, I keep saying 1, A sub I2 times B sub 2j. And you keep going until you get to P. The last term in that summation is going to be A sub IP times B sub pj. Do that addition. That's going to give you the ijth entry over in this matrix here. Now, as K goes from 1 to P, we're looking at A sub I times K. Now, who are those entries? Well, I is staying fixed. And remember, I refers to the position, the row position. So what we will have is in the ith row, we will have A sub I1, A sub I2, A sub I3, dot, 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 dot. Eventually we get to A sub I sub P. All right, so this is the ith row. And then over here, we've got B sub kj. So now j is staying fixed. The first subscript is changing, the second subscript is not. So what we're doing is we're working our way down the jth column of the matrix B. So this would be B sub 1j, B sub 2j, dot, dot, dot. Eventually we get to B sub pj. That is the jth column. And I know this looks complicated. It takes a little bit of time to explain what's going on here. Once you get used to it, it's really not that difficult to multiply matrices, but you have to understand how it works. Okay, so now we want to see, so when we do this operation right here, what it gives us is the ijth entry. So let me call that C sub ij. So what we have is C sub ij, I'm writing for, this is the ijth entry of the matrix A sub B. Now, how do you get C sub ij? It's going to be AI1 times B1j. AI1 B1j plus, okay, what's next? AI2 B2j. And you keep going dot, dot, dot. Eventually we'll get to AI3 IP times BPJ. Right, so that right there tells you how to get the ijth entry of A times B. It's kind of, it's complicated. But one thing that this should remind you of is a dot product. You can think of this, think of the entries of AB as being obtained in exactly the same way that you computed dot products when you were learning about vectors in Math 143. So what are we doing? Take that row vector, that column, think of it as a column vector, and take their dot product. How do you take dot products? You multiply entries in order and then add the results together. That's what this is telling you to do. So if you like, you can think of the ijth entry of A times B as the dot product of the ith row of A with the jth column of B. Okay. All right, so now it's time for an example. So let's say A is the matrix 1, 3, 1 minus 1, 2, 0. Minus 1, 2, 0. And B is the matrix 2, 0, minus 1, 1. 2, 0, minus 1, 1. 2, 0, 3, 2. And 1, 0, 1, 4. 1, 0, 1, 4. All right, so what we have here, A is a 2 by 3 matrix. B is a 3 by 4 matrix. So A times B is going to be a 2 by 4 matrix. There will be 8 entries in there. And so let's compute. So first, I need to get the 1/1 entry right here. How do I get that? I take the first row of A and dot it with the first column of B. So that is going to be 2 plus 5, careful here. 2 plus 6 gives me 8, plus 1 gives me 9. 2 plus 6 plus 1. 9. Let's hope I don't screw this up. Okay, so now I'm going to take, I'm going to move on to the next entry in the first row. I'm going to dot top row with second column. Well, that's going to give me 0 plus 0 plus 0. Now I'm going to do first row times third column. That will be minus 1 plus 9 is 8, plus 1 is 9. Now I'm going to do first row dotted with fourth column. That will be 1 plus 6 is 7, plus 4 is 11. All right, that gives us the first row of A times B. Now we need the second row. So what I'm going to do now is the same process, but I'm going to use the second row of capital A. I'm going to dot it with each of the columns of capital B. So we'll have minus 2 plus 2 is 0, plus 0 gives me 0. Then we'll have 0 plus 0 plus 0, so that's 0. Then we will have 1 plus 6 is 7 plus 0, so we get 7. Negative 1 plus 4 is 3 plus 0, so we've got a 3. Just crashing my chair there. Told you this office is a little bit crowded and cramped, but it seems to be working out all right. So this takes some practice to get used to. The way I think of matrix multiplication, though, is by computing a whole bunch of dot products, right? To get the entries in the first row of A times B, you take the first row of A and dot it with each of the columns of B in order. That will give you the first row. To get the second row of A times B, you take the second row of A, dot it with each of the columns. That will fill out the second row. If there were more rows of A, you would keep going, dot them with the entries in B, or with the columns in B. That will give you the entries in the successive rows. Okay, so we've defined this idea of matrix multiplication, and now what I want to do is elaborate on it and talk about some operations, things that are connected to matrix multiplication. Okay, so and let's this is an important definition here. So if A, we'll call them A1, A2, these are all capitals, up through A sub, let's go to A sub K. If each one of these I want to be a matrix, an m by n matrix. So if these are m by n matrices, and C1 up through C sub k are scalars, or real numbers, then we can look at C1 times A1 plus C2 times A2 plus dot 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 plus C sub k times A sub k. Now, when you do this, what are you going to get? Well, this will be an m by n matrix. This will be an m by n matrix. Each one of these will be an m by n matrix. And when you add it together, it will be an m by n matrix. The result right here is called a linear combination. So when you take matrices, multiply each one by a scalar, and add the result together, that is called a linear combination. So this is a linear combination. So, for example, you could do, I'm just going to look at 2 by 2 matrices. So 3 times 1, 0, 0, 1 plus 2 times 1 minus 1, 4, 3 plus negative 1 times 1, 2, 0, 0. There's an example of what we call a linear combination. Now, there's an especially important case. I'd say the most important case, right? One that we're going to see lots and lots of, is in the case that each of these matrices right here is actually a column vector. So let's say most important case, when each AI, A sub I, is a column vector. All right, so for example, 3 times 1, 1, 1 plus 2 times 0, 1 minus 1 plus negative 2 times 0, 1, 1. Now, when you do this operation, what are you going to get? The top entry would be a 3. This will be 3 plus 2 is 5 minus 2 gives me 3. And then 3, all right. Okay, so then we'll get 3, 3, 3. This stuff right here, I guess, did it just cancel itself out? Oh, no, wait a minute. Minus 1, that would be negative 2. Oh, no, sorry, that would be 3 plus negative 2 gives me 1 minus 2 gives me a minus 1 in that bottom entry right there. Okay, so we're going to continue talking now. I want this all to sort of connect up with, in fact, what we'll see is that this is going to connect up with matrix multiplication. So let's say now that we've got an n by n matrix. So A is, I'm going to actually write out the entries here. So A11, A12, dot, 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 A1n, and we'll have an A21, A22, dot, 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 A2n, and eventually we get to the last row, AM1, AM2, dot, 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 AMN. Right, so there's our n by n matrix. And then I want a column vector, and I'm going to write this, so this is going to be x equal to, and I want it to have the entries x1, x2, dot, 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 down to x sub n. So what we have right here, we've got an n by n matrix here, and we have an n by 1 matrix here. Which means that it's legal to multiply these matrices together. A times x. What's it going to be? It's going to be an m by 1 matrix, right? So let's write this out now. Let's see, so how's this going to work? So let me write it out like this. I'm going to kind of do the details here. The top entry will be this row dotted with this column. So that's going to be, okay, so it'll be A11 X1 plus A12 X2 plus dot, 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 plus A1N X sub n. So there's the first entry. Remember, this is just a single entry. This is actually a skinny column vector, right, once you do the arithmetic here. Then we will have A21 times X1 plus A22 times X2 plus dot, 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 plus A2N times Xn. And you keep going. Eventually what we'll have is AM1 X1 plus AM2 X2 plus dot, 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 plus AMN Xn. Okay, now I'm not done. I want to finish this off. But so here's the original computation. And here's what you want to notice. If you look right here, what you have is X1 multiplied by the entries of the first column of capital A. Scalar multiplication, X1 times the first column. And then, if you look at this next portion right there, that's X2 times the second column of A. So we've got X2 times A12, A22, dot, 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 AM2. And you keep going, what you'll notice is that multiplication, this matrix A times this column vector, can be expressed as a linear combination of the columns of capital A. Oh, so this last one should say plus X sub n times the last one here. So this would be A1n, A2n, dot, 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 AMN. So this is important. What you can see is that when you do matrix times column vector, it can be expressed as a linear combination in this fashion right here. Now, the nice thing is that this all connects back up with linear systems. And so, let's write it like this. So connection with linear systems. So I want to work with the same A and the same X that we had before. So with A and X as above, or as before, and B, I want to write it like this, B1 dot Bn. Here's the nice thing, is we can phrase our linear system in terms of this matrix multiplication that we just had. The linear system and so it'll be our standard one. I'll write this out. So this is A1 1 times X1, A1 2 X2 plus dot 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 plus A1n Xn equals B1. A12 X2 plus A22 X2 plus dot 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 plus A2n Xn equals B2. This is the same one that I labeled as star, and I said I'm never going to write this down again, I'm just going to use star, and now here I am writing it down. M1, oh, something's wrong here. What did I do wrong? Oh, that should be a 2, 1 there. A M1 XM plus a M2 X2 plus dot 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 plus a M n xn equals b sub n. Right, so here's our system that I usually label as star. This can be expressed as, not at, a times x equals b. So it gives us a nice compact way to write our linear system. It gives us a connection between linear systems and matrix multiplication, so we can write this linear system as a matrix equation like this. And that's a good thing. This right here, so capital A is the coefficient matrix. There's a couple more operations that I want to talk about. So let's say 2 more operations. So the first one, so let's say if A is m by n, the transpose of A is the n by m matrix, which is usually indicated capital A sub t, defined by the ijth entry of the transpose is the jith entry of the original matrix. So what this is saying, starting off with matrix A. To get this matrix called the transpose, you interchange the roles of row and column. So the rows of A are in order the columns of A transpose, and the columns of A are in order the rows of A transpose. Hope I said that right. So let's do an example just to make it clear. Let's say that A is the, how about let's go like this, 1, 2, 1, 0, 3, minus 2. All right, so there's A. It's a 2 by 3 matrix. A transpose is going to be a 3 by 2, and so the first row of A transpose is the first column of A. The next row will be 2, 3, because that's the second column of A. The third row of A transpose will be the third column, so it'll be a 1 minus 2. Right, so interchange the roles of row and column, and you've got the transpose. Right, and there's a 3 by 2. In the case that we have a square matrix, there's another operation. So if A is n by n, the trace of A is, and it's usually written TR of A. And the way you get this, remember, if we have n by n, then there's this thing called the main diagonal. To get the trace, you add the entries from the main diagonal. So that will be A11 in parentheses, plus parentheses around A22, plus dot dot dot, plus A parentheses NN. So if you've got a square matrix, to find the trace, add the entries along the main diagonal. So for example, if A is 1, 2, 3, 4, then the trace of A, take the entries along the main diagonal, that's 1 plus 4, which is 5. The trace is not an operation that's going to come up a whole lot in this class. It does come up occasionally, but not too much. Okay, so I want to end with just a few observations about matrix multiplication. So let's say some observations. Let's say, suppose A is m by p with, let's say, rows R1 up through R sub m, and B is P by N with columns C1 up through C sub n. So the first observation, the ijth entry, and we said this already. I mean, I talked about matrix multiplication and in terms of thinking of it in dot products, or as dot products. The ijth entry is obtained by taking the dot product R sub I dotted with C sub j. So that's a nice way to think about it. Or, you know, maybe it's better, I mean, this is a row vector, this is a column vector. I think maybe, you know what, I'm going to do this. Think of it like this so that they're both row vectors. R sub I dotted with C sub j transpose. Right now now that dot product makes a little more sense as dot products of row vectors. And two more facts. The next one. So let's see. The jth column of AB is A times C sub j. And then the last fact, so this is another way to think about how to find the entries of A times B, right? You can do it column by column. The jth column can be found by doing A times C sub j. The ith row of A times B is R sub I. Did I write that right? Yeah, R sub I times B. Okay, so that was kind of a long lecture. There's a lot to digest here, but these are the matrix operations that we are going to be working with for the rest of this class. They are all important. In particular, matrix multiplication is extremely important.